Okay, let's continue our program of soil mechanics. Let's start with the chapter number 2. Okay, I think this one is the French version. Let me change it. Okay, this is the English version. The French version also will be available. So if you want, you can check it. I will put the link in the comment so that you can find it. Okay. So in this video, we will start the chapter 2 of this program. And for this chapter, I think we will do maybe at least 2 videos for this chapter because it's longer than the previous one. Okay. So chapter 2 is about the origin of soil and the grain size of soil. So in this chapter, these are the points we will talk about: introduction, rock cycle and the origin of soil, rock forming mineral, rock and rock structure, soil particle size, clay mineral, specific gravity, mechanical analysis of soil. This one is very important. And particle size distribution curve. That one also is very important. This one and the last one is particle shape. How all these parameters will influence our design in geotechnical engineering. Okay, so let's start with the first point, introduction. Here, this introduction, in general, soil are formed by weathering rocks. So it means weathering of the rock induce the formation of soil. Okay, so physical property of this soil obviously will be influenced by the rock. Okay, so the mineral that were in the original rock from which the soil is formed, those minerals will definitely dictate the property of the physical property of the soil. So in this chapter, we will explore this following point. First point is the formation of different type of rock. Okay. Second point is the process of soil formation through mechanical and chemical weathering of rock. Because there are many types of weathering. Okay. Mechanical, chemical weathering of rock. So understanding distribution also of the particle size of the soil. And this point also we will try to do it. Composition of clay mineral and their influence on the plastic property of the soil. And the last one, we will examine, we will do by investigating or studying like shape, different shape of soil particle. That one is the last point of this chapter. So let's start with the first point, which is cycle, rock cycle and the origin of rock. Okay. The solid phase of soil aggregate is composed of mineral soil, which are the result of rock weathering. The size, shape, chemical composition of these grains play a significant role in determining the physical property of soil. The grains are better to gain a better understanding of these factors. It is then important to to be familiar with fundamental type of rock that make up the near surface of Earth. Minerals that form these rocks and the process of weathering. We need to understand all this. So we have generally like 3 primary types of rock based on the mode of origin. So we have igneous rocks, sedimentary rock, and metamorphic rock. The formation cycle of these different type of rocks and the associated process are shown in this figure. For example, we can see here for magma in the underground, deep underground, can give the igneous rocks. And this, by transportation, erosion, and weathering of these igneous rocks, we can obtain some sediment. Okay. And also we can do it backward also, from sediment to rock. And also, this sediment can give also another type of rock, like this way, by compaction, cementation, and crystallization. From this sedimentary rocks also, we can get another type of rock, which is metamorphic rock. And by melting this kind of rock, we can get magma. So this is cycle of rock. And this process is actually, people are doing it now in a lot of laboratory, obtaining this type of rock by using just cementation of soil, of sand, for example. Here is an example. And I know one professor who is doing this in Hokkaido University. This is like sand, and by using bacteria, they can make this sand to be cemented and become like this semi-sand column. Okay, so this exists now. Artificially, we can do it by just using bacteria, and the process is called biocementation. You can try also. Okay, let's move to the third point of this chapter: rock forming mineral, rock, and rock structure. This figure 3 shows the common rock forming mineral, which include quartz, autoclase, plagioclase, muscovite, biotite, andradite, and all these minerals are the mineral we can find in rock. Okay, dolomite, chloride. And this figure shows the types of rocks. Previous one is just mineral we find in rocks, and this one is the rocks, different types of rock we can find as geotechnical engineer. We can encounter in the field. Okay, a lot of them: granite, basalt, rhyolite, sandstone, limestone, conglomerate here, marble, slate, and schist. All these type of rock are the rocks we have to deal with during sometimes geotechnical, during construction projects. So there are large structures built several centuries ago. Previous one is, this is just rocks. Okay, now we are talking about rock structure. we have a lot of structure built with rocks, in rocks, or on rock. Some of them are still existing and are intact, are not damaged. But some also are undergoing weathering, so are being damaged by weathering. Okay. So this, for example, this Parthenon, I think in Greece, this was built in the second half of the 5th century before Christ, so long time ago. So it made of marble, so means this the material is marble, and it's being built on limestone hill. So this hill is a limestone, and under this limestone we have phyllite, a fine grained metamorphic rock that contain large quantity of mica and resembling slate or schist under this. This one also in Greece, this channel was also completed in 1893. So as you can see, it also around here, it's just rock. We didn't use any concrete or something to make it stable, just rock, and it's stable since 1893. So it consists of single channel, 18 meter deep. It's quite deep actually, and excavated at sea level. So it measures 6,346 meters. So it's more than 6 kilometers. That's very long. And the large of 24.6 meters at the top. So means at the top we have around 24.6 meters. And the bottom maybe 21.3 meters. So the central part of this channel were excavated slope are where the slope in the middle, the slope are highest. That part consists of this type of marble with thin interlayer of marbly sand and marly limestone. Okay, so all these structures are just built in, on, or with rocks. So this one is built with rock, and it builds also on rock. That's the end of this part 3. Let's move to the part 4, which is soil particle size. The soil are typically categorized as we can see gravel, sand, silt, or clay. Okay, so based on the predominant particle size, we decide that our soil is gravel, it's sand, silt, or clay, just based on particle size. Okay, so there are various organizations that have developed a classification, particle size classification, which are displayed in this table. We can see here MIT, US Department of Agriculture, American Association of State Highway and Transportation Official. And this one, unified soil classification system. We have here, each of them has its own classification, but they're all based on the size of the soil particle. Okay, for example, this one is saying if the particle is, maybe diameter is higher than 2 millimeter, it's in millimeter here. Okay, so we consider it gravel. Between 2 and 0.06 millimeter, it's sand. From 0.6 to 0.002, it's silt. And clay is particle size less than 0.002 millimeter. Okay, so this one, the Department of Agriculture of US giving quite different definition, and this one also different definition. But despite we have a lot of them, this last one, the Unified Soil Classification System, is widely accepted and is used in many countries. Actually, to be honest, a lot of countries are just copying this American codes and everything, and they're just adding some little things. So this is widely accepted, the Unified Soil Classification System. So you better know it. This figure shows also this classification in a graphic form, the same classification we have seen in the table, the previous table. Okay, you can see here, this is gravel, and this is like sand, and silt. Silt is here, silt and clay for this unified system, and this is clay. This is silt, this is clay. But here they are saying just fine. The fine are just grain size, the minimum one, minimum grain size. Okay, so as we can see here, gravel are like maybe it's not shown here. I will show it later in photo. A fragment of rocks, and the particle in this gravel are we can find sometime particle of quartz, feldspar, and other mineral. But the main thing you should know is just a fragment of rocks. Okay, so this photo show some gravel. You can see idealize the size, the grain size. Sand is consists of particle mostly of quartz and feldspar. Okay, and we can find other mineral grain. Here is an example photo. This photo show the sand. I think everyone knows. Silt also are like very small microscopic soil fragment. We can find also very fine quartz grain, flake-shaped particle. This photo shows what we call silt. This is example, typical example of silt. And the last one, clay, also very is flake-shaped microscopic and submicroscopic particle of mica, clay mineral, and other mineral. This photo shows clay. And I think silt, we have to to insert silt in this classification because the difference between sand and clay is very important. They're quite different. So this silt is somehow the intermediate between sand and clay. Okay. I'm not saying that this silt is mix of the mixture of sand and clay. No, no, no. But it's just the intermediate between these two. Because the behavior of clay and behavior of sand are very different, completely different. So we had to find another name for this type of soil. Okay. Okay, according to the table and the graph, the diagram we saw before, clay are typically defined as particles smaller than 0.0002 millimeter. This is definition based on the size, the particle size. Okay, but actually, some particle in this size from 0.002 to 0.005 millimeter are not clay mineral actually. Okay, so in some cases, particle ranging from 0.02 to 0.005 millimeter, we can also call them clay. Yeah, but we should not forget that this classification is based on the size, the particle size, but it doesn't mean that the particle are necessarily containing clay mineral. So clay are normally particles that exhibit plasticity when we mix them with small amount of water. That is clay mineral. If you add a small amount of water in clay mineral, the clay can behave like plastic. This is example. So some art made from clay, just adding some amount of water and you can work with clay. This is bust and this is car made from clay. So non-clay soil can contain also quartz or feldspar or mica particle that are small enough to fall within the clay classification. That means they are non-clay, but dimension are within this smaller than 0.002. But they are not clay mineral, okay? So in that case, it is more appropriate to refer the soil particle smaller than 2 micron, which means 2 millimeter, or 5 micron as clay-sized particle rather than clay. So this particle smaller than 2 micron, we should not normally say that they are clay. The right name is clay-sized particle. This is the right name we should say, because not all of them are clay mineral. So clay particles are predominantly in colloidal side range, within 2 millimeter being the upper limit. The upper limit is 2 millimeter for the clay. Okay. The part number 5 of this chapter now. Clay mineral. This part also is maybe important. In this part, we will learn how how clay behave when you add it with water. When you mix clay with water, how clay will behave. And so the clay mineral consists of silica tetrahedral and aluminum octahedral unit. Mainly these two. So this silica one contain of 4 atoms of oxygen surrounding a silicon atom, which is shown here. For example, 1, 2, 3, 4 atoms. These are atoms of oxygen, and in the center we have a silicon atom of silicon. On the second hand, the aluminum octahedral one consists of 6 hydroxide surrounding 1 atom of aluminum. Then you like this is shown like this. This one is 1 atom of aluminum. I think 1, 2, 3, 4, 5. Maybe this one make it 6 normally. And in the middle we have 1 atom of aluminum. So the combination, when we combine now this unit, okay, we can form silica and gypside sheet. Okay, when you see here, this is 1 tetrahedra. If you put them together, many of them, it will make a silica sheet. Okay, here also. So just putting together many unit, we obtain sheet. So these are also known as silica sheets and gypside sheets. Okay, so in some cases, for example, here, magnesium can replace aluminum and sometimes even iron. This blue point here, now they are aluminum, but we can replace them by magnesium and iron sometimes. But in that case, if it is magnesium, we don't call them gypside sheet, but we call them brassite sheet. Yeah. So in the silica sheet, each silicon atom is linked to four atoms of oxygen, like I explained before. On the top oxygen atom of each tetrahedron has negative charge of 1 to balance the positive charge of the silicon. So this means the silicon has positive charge, and at the top, this one, we have so that will balance the charge. Okay. So this one has negative, and this silicon has the positive. So positive and negative to balance the charge of this silicon. Okay. So when the silica sheet is stacked over the octahedral sheets, like this, for example, so we put this one on this one. In that case, the atoms of oxygen of this silica sheet replace this hydroxide to balance the charges. Yeah, something like that. This kaolinite is one of the clay mineral that consists of repeating layer of silica gypside sheets in a 1 by 1 lattice. So each layer is about 7.2 Armstrong. If I mean, I think this 10 minus minus 10 power minus 10 meters. So these two are held together by hydrogen bonding. This is, for example, in this case. So we have this silica sheet and gypsum sheet, and the two, we have hydrogen bonding between these two, and the thickness is 7.2 Armstrong. This is a photo of this kaolinite, which is, people are eating this. Some people eat this actually, kaolin. And the second one, illite, also known as clay mica, has a gypsum sheet bound to two silica sheet. So one gypsum, one gypside sheets and two silica sheets. So the illite layers are bound by potassium ions. So we can see here two silica sheets and one gypside sheet, and between two we have potassium. And this last one, the monorilonite, something like that. I'm not sure how to read this. And this one is this is a photo of the illite. And the last one has also similar structure to illite, but with isomorphous substitution of magnesium and iron for aluminium. So this means the aluminium is replaced by something else, magnesium or iron. And the water is attached to the space between the two layers. For example, here we have n molecule of water, H2O. So to attach, it's similar to this one, but here we have potassium. Here is a photo of this type of mineral, also the clay. There are other minerals also we didn't show here. These minerals all also exist as the previous one. They are very common also. Clay particles carry net negative charges. The surface of clay, we have negative charges on the surface, and the positively charged site can also occur at the edges of the clay particle. So in dry clay, the negative charge is balanced by exchangeable cation, like this say A2 plus, Mg2 plus, and A2 plus, Na plus, and K plus. So this cation surrounding the particle being held by electrostatic attraction. So what happened now when we add water to clay? Okay. So from here, we will talk about the mechanism by which water is attached to clay particle. So when we add water in dry clay, as I said in the previous slide, the clay mineral has negative charge, and also we have some cation. So when we add water, this cation, I'm talking to this cation, like this. After adding water, this cation and few anion will float around the clay particle after adding water. This configuration is referred to as diffuse double layer, as shown here. So the clay particle are like this, negative charges. And after adding water, we will have some cation. The anion we saw in the previous slide, and some cation. This cation and some anion. These are cation, positive charge are cation, and anion, negative one. Okay. So we have this balance between cation and anion. So the cation concentration decreases with the distance from the surface of the particle. So this is explanation, another explanation. After adding water, we see that this molecule of water, they have also charges. This oxygen has minus and hydrogen plus. So all these interact with the cation and anion in the clay, and of course the surface of the clay, which is negative, and some positive at the edges. So the second mechanism is like after adding the water, we know that water molecules are polar, hydrogen atoms are not axisymmetric. So around an oxygen atom. Instead, they occur at a bounded angle of 105 degrees. Like this figure, sorry. So this angle is 105 degrees. We have hydrogen here, and oxygen here. So as a result, the molecule of water has positive charge, which is this oxygen at the one side, and negative charge at the other side. Like here, all these are molecules of water. Positive, negative. So this is known as a dipole. So dipolar water is attracted both by negative charged surface of clay particle. So we have this negative charged surface of clay. Of course, the negative part of water brought by hydrogen will be attractive to here. For example, plus and minus attraction. Okay. And also by cation in double layer. We have talked about this cation previously. So the cation will be attractive with the negative part of this water molecule. Something like that. So the cation in turn are attached to the soil particle. Third mechanism Third mechanism by which water is attached to clay particle is hydrogen bonding. Hydrogen bonding, where the hydrogen atom in water, this hydrogen plus plus, are shared with oxygen atom on the surface of clay. So some particle hydrated cation in the pure water are also attracted to the surface of clay particle. So this cation attract dipolar water molecule. We have here this figure shows the force. This figure shows water trapped in clay particle, for example. We'll talk about this, how it works exactly, and the names of this water in the clay particle. So the force of attraction between water and clay decreases with distance from the surface, of course, of the particle, okay? So all the water held to clay particle by force of attraction, this water is known as double layer water. Double layer water. And the innermost layer of this double layer water, which is held very strongly by clay, is known as absorbed water. And this absorbed water is more viscous than free water. This, what I was talking about, this two, this showing us what we call absorbed water. And this one is, I think, for kaolinite, and this one, maybe, I'm not sure, montmorillonite. And this orientation of water around the clay particle gives clay soil the plastic property. So, as I told you before, when we add a certain amount of water in clay, the clay becomes plastic. So this is because of this orientation of this water, okay? This absorbed water. This presence of mineral, the presence of clay mineral greatly influence the engineering property of soil. So we have to be careful if there is any clay in soil. So in particular, when the content, the clay is high, the content of clay is high in the soil. So when the moisture is present, the engineering behavior of soil will change greatly as the percentage of clay mineral contained increases. So if when there is clay, once we have small amount of water, like rain, for example, it will give a big influence on the geotechnical property of the soil. So for example, in practice, when we have, for example, 50% or more for the content is clay, if the 50% of content is clay, the sand and silt particle float in the clay matrix, and the clay mineral primarily dictate the engineering property of the soil, which means once the content of clay is 50% or higher, we almost consider the soil as clay, because the behavior will be almost same as the behavior of clay. Yeah. So this is the end of this section, clay mineral. And this one now, I think from here, it will become more interesting. Right, specific gravity of soil. What is specific gravity? Okay, it's very simple. Specific gravity is just measure of that compare the unit weight of soil material and the unit weight of water. This is just like a ratio. So we can measure this specific gravity in laboratory. And this table is showing specific gravity of some common mineral found in soil. You can see quartz here, 2.65, kaolinite, 2.6, illite, 2.8, and so on. So the most of these, the value range from 2.6 to 2.9. And for instance, light colored sand, you have sand, which contain mostly like quartz, can be estimated to have a specific gravity of approximately 2.65, same as this quartz. So the clay and silty soil may have specific gravity value range from 2.6 to 2.9. And these values are usually for assigning the property and behavior of soil in engineering application. So we need this value in engineering application. So we better know this. And don't ask me why there is no unit, because this is like a ratio. It is like we divide the weight of soil divided by the weight of water. As you know, weight of water is constant. Maybe you can say 1 kilo, about 1 kilogram per liter, something like that. Yeah. So by dividing the weight of soil by weight of water, you obtain what we call specific gravity, KGS. Yeah, that's also the end of the sixth section. So I think we will stop here for this video. The next one, from the next video, it will be more interesting. So please follow this program if you want to learn. And if you are learning French, the French version of this video, you can get the French version of this video also and train yourself. Okay. Thank you very much.